Thank you for
Thank
your
you.
amazing presentation. So we will move on. We will continue with Fatema. Fatema is from Germany, TU Clausthal, and she's going to talk about modeling interaction of pedestrians and cars in shared spaces. So thank you, Fatema, for joining, and you can begin your presentation.
Thank you, Dr. Akim, for nice introduction. Hello, everyone. I'm Fatema from University of TU Clausthal, Germany. I'm a PhD candidate here. Today, I'm going to give a brief introduction about my research, which is titled Modeling Interaction of Pedestrians and Cars in Shared Spaces Using Game Theory. Shared space is an alternative of traditional traffic design where there are different types of road users coexist, such as pedestrians, cars, bicyclists, with few or no explicit traffic regulations. Therefore, no clear priorities among road users, so they have to interact more frequently with each other, and their interactions are mainly handled by social protocols like courtesy behavior and informal rules. The use of shared space design principle is increasing, even though there are ongoing debate on the safeness and efficiency of shared spaces. Therefore, the estimation of shared space traffic performance is critical, and good simulations models are needed for that purpose, which can be also used for autonomous car as a safe basis to learn how to interact with other road user types. However, modeling mixed traffic like shared spaces is very challenging because the simulation model should capture the complex decision makings of heterogeneous road users and also the uncertainties due to the lack of traffic regulations. The previous works on modeling and simulating shared spaces are mainly based on the social force model, which is a physics-based model, which is mainly for modeling pedestrian dynamics, but many researchers already extend this model for mixed traffics also. The contributions of my research are the threefold. First of all, I propose a novel motion model of pedestrians and car, which can simulate or reproduce a large variety of interaction scenarios like multiple interactions between pedestrians and cars and interdependent interactions, so on. And it can also recognize interactions based on the situation context and also transferable to different environmental settings. To do so, I combined a game theoretic approach with a social force model, which is inspired by this author, and my model is named Game Theoretic Social Force Model, in short, JSFM. Together with one of my colleagues, we also propose a hybrid model of JSFM and a deep learning model. And together with Dongfang Yang, we also propose a method for recognizing and modeling of different behavioral patterns of pedestrians, which I will, the third contribution I will not discuss today, as Dongfang mentioned some brief information about that already. Okay. So to model JSFM model and the hybrid model, I follow the following three methodology. At first, I start with detecting, analyzing, and classifying typical interactions in shared spaces through video observations of real world data sets and also the literature review. Currently, I'm only working on pedestrians and cars. So the typical interactions in shared spaces can be divided into two categories. A simple interaction, that is the direct mapping of perceptions to action, and can be also classified to complex interactions where road users at first perceive the environment and choose a decision among alternatives and then act. Like in this crossing example, the pedestrians have different alternative decisions to avoid conflicts with these two cars. If a conflict involves more than two road users, we divide them into these two categories. One is called multiple conflict, where let's say these pedestrians have two concurrent interactions with both of these cars, and this same conflict can be called multiple user conflict if the both of these two cars also need to interact with each other. That means that all the participants of a conflict situations are codependent. The interactions can be also classified based on the number of road users involved and also the type of the road user. The interactions between pedestrians and car also differ based on the environment types. So far we consider road zone and intersection or roundabout like areas. How we analyze and model the zone-specific behaviors of pedestrians and cars, and the more details you can find in this paper. The JSFM model is combined with three different modules, namely trajectory planning module, force-based modeling, and game theoretic decision making. Trajectory planning module is responsible to calculate the free flow trajectories of road users. We use A-star algorithm to calculate the shortest path, that is the free flow trajectories of the road users, only considering the static obstacles. And the force-based module is responsible to handle simple interactions and also the actual execution movement of road users. And the game theoretic model is responsible to handle the complex interactions. And JSFM model also have another element, which is a BDI controller, which is responsible to handle the workflow among these three modules. I will explain the force-based modeling and game theoretic decision making in details in the later slide. So as I mentioned earlier, that we use the social force model, which is a combination of some simple forces to conduct pedestrians movement. The forces are namely the force towards the destination of pedestrian, the force the pedestrian get from other pedestrians or wall or boundary. Then we extend the social force model by adding group behavior, pedestrian group behavior, which is also combined of two different forces, the visibility force and the attractive force. The visibility force is that the group members want to see all other group members, want to keep all other group members in their field of view, and the attractive force is they want to stay together. We also extend the social force model for vehicle movement by adding following behavior and the emergency stopping behavior of cars. And we use a Stackelberg game, which is a sequential leader-follower game, to handle complex interactions. In Stackelberg game, the leader, there is a leader and a follower and a set of followers, one or more. The leader at first choose a decision by predicting the best decisions or best answer of all the followers, and then choose the best strategy that will give him or her the highest utility. And then the followers will choose a strategy that optimizes their utility. In Stackelberg game, there can be a single leader, but more than one followers. We choose the faster agent, here the car, as the leader. And in the situation where there is more than one car, the one who recognized the conflict fast considered as the leader. And to calculate the payoff metrics for the game, we at first did some ordinal valuation of outcomes with the assumption that all the road users want to reach their destination safely and quickly. We also consider impacts of situation dynamics. We consider the following factors like current active behavior of or the current speed of target and competitive road users. We examined these factors and also calibrated their parameters accordingly. Here is one example scenario to show how these three modules execute, or the workflow between these three modules. So in the beginning of simulation, the trajectory planning module at first planned the free flow trajectories for all road users And then it gives the responsibility to the force module to calculate the execution of the movement of all road users until they detect a complex conflict. Then now it's a task for the game module to make a decision or a strategy pair for the participants. Let's assume in these situations, the decision for the car is to decelerate and the pedestrians will continue. So now the game module will give the responsibility back to the force module to actually execute these decisions. The BDA controller here can prioritize the decisions of force-based module and game module based on the current situation. We calibrate our model parameters with performing simulation-based calibrations or using a genetic algorithm. We have a large set of parameters. So we calibrated the social force model parameters and the safety parameters like the minimum distance maintained between pedestrian and cars by minimizing the difference of simulated and observed trajectories as the fitness. And to optimize, to calibrate the game parameters, the algorithm try to minimize the difference of simulated, that is the game theoretic decision, and the observed decision as fitness. To evaluate our model, we perform several experiments. We at first evaluate our model qualitatively. We also compare with the deep learning model and evaluate also the model transferability. So here is one complex scenario, road crossing scenario. The pedestrian need to interact with both of these cars to avoid collision or and the pedestrian want to cross the road. In the real scenario and also in our simulation model, in both cases the pedestrian wait and both car continues. This is another example of a complex scenario where a group of pedestrians is trying to cross the road and the two car is also trying to go through the roundabout. And in this scenario also, our model reproduced the scenario. However, in both this scenario, although the behavior, our model predict the behavior of road users accurately, but it failed to mimic the speeding profile of the real road users. The next, we I compare my model with a deep learning model implemented by one of my colleagues, and here I present the main differences that we found. The motivation was to find the strength and weaknesses of both of this model. And as you can see in this picture, that the LSTM, that the deep learning model, predict the road user's trajectory more accurately than the GSFM model. However, it cannot always guarantee collision-free trajectories. Another thing to mention here is that the performance of the deep learning model drops more drastically than GSFM for long-term prediction. So to overcome these weaknesses of these two models and work on their strengths, we also proposed a combined model to where we take the advantage of my model, the guaranteed collision-free trajectories, and the advantage of the deep learning model, which is a prediction of heterogeneous movement behaviors. More details can be found in the paper. To check the transferability of our model, like if our model can work from different environment settings, we check the performance of our model in a new data sets. Whereas our model was built on and also calibrated on HPS dataset, we check the performance of our model in duty dataset. And as expected, the performance drops in the new dataset because these two datasets are very different from each other based on the environment structure and type of the density of the environment and also social norms. But by adding only few social norms into our model, we get satisfactorily improved performance for the new data sets also, which also conclude that our model have the ability to transfer from one environment to another. To conclude, so far I proposed a novel motion model for pedestrians and cars, and we propose a combined model of JSFM and a deep learning model. And I didn't talk about this other contribution, which is propose a method for recognition and modeling of different behavior patterns of pedestrians. And for future work, I will look into the estimation of traffic performance of shared spaces using my model, and also integrate new modalities, which is a bicyclist, to my model, and also work on the improvement of our hybrid model. Thank you for your attention. And if you have any question, please feel free to ask, and you can also send me email or can also read the papers for more details. Thank you.
Thank you, Fatima. We have 3 minutes and we have 2 questions. The first question is from an application side. How do you think these pedestrian trajectory predictions might be used? For example, will it change the trajectory planned by an autonomous vehicle? Or will it be fused with visible camera data to improve object tracking? Or will it change intersection signal and timing, and so on? What do you think?
So as I mentioned earlier, that I'm working on the shared spaces where there is no traffic light or regulations. So the main motivation of this model is that the model can be used at first as a decision model for autonomous car. Like you can model the scenarios which you cannot get, it's not available in real data sets. Like if you have a question in mind, like what if a pedestrian jump in front of a autonomous car, how do the autonomous car will react? You can see this kind of what if situations in realistic and improved simulation model. So this is another purpose of this simulation model, and the other purpose, as I mentioned earlier, is to estimate the traffic performance of shared spaces. So try different design of shared spaces and which is more efficient for before actually applying these shared spaces, which is costly.
Thanks, Fatima. We have one more from Taewon Han. Why do you always consider cars and not the pedestrians as a leader in slide 11?
Here I only show the one that give me the most accurate result. Actually, I tried
slide 11. That question was specifically about slide 11.
Okay, I don't know, my screen
okay.
somehow hang or something. Okay, I try to go here.
And we have 1 minute. So
yeah, this was an example scenario, but I understand your questions. Like I also tried the selection of leader randomly, and also tried leader pedestrians as leader. And after the experiments, the car as the leader give the more accuracy. That's why I keep using car as a leader. But as the parameters or the factors to calculate the payoff matrix, it's calibrated. So it's the pedestrian also get priority. It's not like always the car get the priority because car is the leader. So not always the car get the priority. So pedestrian also get the priority because the parameters are calibrated using the
thanks,
real
Fatima.
world.
We finished our allocated time slot, but if you can give one more answer to a short question. The question is there any study done which can differentiate between pedestrian movement because of the size and type of the vehicle? When you have a truck or a regular passenger car, is there any difference? Is there any study?
There should be a difference, and that can be done, but so far I didn't do that. But my model is based on a multi-agent based framework, and in multi-agent based framework you can give different properties of the agent. You can give the different size of the agent and try to run the same model
Okay, thank you, Fatima. We ran out of time. That was a great
Thank you.
presentation.
Thank
Thank you. And for our audience, you can ask more questions using the Q&A tab, and we can answer them after we finish the main session.